Hello and welcome back. In this video, we're going to further our discussions on standing waves, which we began talking about in Chapter 16. So Chapter 17 covers sound, and standing waves have a lot to do with musical instruments, which we are all fans of. So the boundary conditions dictate which frequencies resonate or create standing waves or harmonics on different instruments. So resonate is the same thing as creating standing waves, and those standing waves are known as harmonics. So we're going to have guitar strings or stringed instruments. I'm going to just say guitar here, but it's the same for violin or any fiddle, any other stringed instrument. The boundary conditions are such that the ends or the boundaries must be nodes. So recall from Chapter 16, we saw that the ends are tied down. The ends are places that don't move up and down. Those are called nodes. So the boundary conditions for a stringed instrument is that there must be nodes at the boundaries or the ends. Boundaries, ends means the same thing. For air columns, these would be flutes, clarinets, tubes, anything that you're blowing air into. Closed ends must be nodes and open ends must be antinodes. So these boundary conditions, the conditions at which the ends of these instruments must satisfy nodes or antinodes depending on what it is, totally dictate what harmonics we hear on that instrument. So let's first of all look at the guitar string of length L. So here's our guitar string, and it's fixed at both ends. So these are nodes at both ends. What waves can be standing waves on this particular guitar string of length L? Well, the largest wavelength would be one that fits exactly half a wave between the two supports. So rises, reaches the support, reflects, reaches the support. So the primary or fundamental wave that can oscillate is going to correspond to the fundamental harmonic, and its length is 2L. Notice I'd need to make the length of the string twice as long to get one full wavelength on there. And so that's going to correspond to a frequency. Remember, frequency is wave speed divided by wavelength. So V is the speed of the wave on the string, and that's going to have a lot to do with what tension that you have this string under, and also the mass per unit length of the string itself. So the speed of the wave divided by the wavelength, and that is 2L. What about the next largest wavelength that can create a standing wave on this guitar string of length L? Well, it's going to be the pink one. So it rises up, comes back down through a trough, and reaches the opposite end. So that's one complete wave and then reflects back. So one complete wave would be the next largest wavelength. So lambda 2 is going to have a length L and correspond to a frequency F2 of the speed of the wave divided by the wavelength L. So notice that F2 is twice F1. And in general, for the nth harmonic, F sub n is equal to n times F1. All of the successive harmonics are multiples of the fundamental harmonic F1. So n is corresponding to the nth harmonic. Now in the middle here, we're considering an air tube that is open on both ends. So remember, when we have air columns or air tubes, and the open ends have to have boundary conditions that are antinodes. So at the ends, I need antinodes. So what is the largest wavelength that I can resonate as a standing wave in this air column that fits the boundary conditions of having antinodes at either end? Well, that would be a wave that rises from a crest, goes through zero, and goes to a trough. So notice that that is exactly half a wavelength and I would need another distance L to complete the entire wavelength. So the wavelength of the largest wave that can create a standing wave or resonate on this tube has a length 2L. That corresponds to a fundamental frequency then of the wave speed. And notice this is going to be the speed of sound in air, because the wave is actually traveling in air here. Here it was traveling on a guitar string. Here it's traveling in air. So it's going to be the wave speed again divided by the wavelength, which is 2L. So this is the fundamental harmonic. What about the next largest wavelength? Well, I've drawn it in pink, and you see we come from a trough through 0 up to a crest, back through 0 to a trough. That's one full wavelength. So lambda 2 then is L. That corresponds to a second harmonic that is V over the wave speed over the wavelength L. So notice that that also is twice the fundamental harmonic. So in general, all the harmonics oscillate, and F sub n is equal to n times F1. So if you want the fifth harmonic, you would have 5 times the fundamental harmonic. If you want the eighth harmonic, it would be 8 times the fundamental harmonic. So all of the harmonics that oscillate are integer multiples of the fundamental harmonic. So these two very similar. All even and odd harmonics oscillate within both of these instruments, open-ended tubes and the stringed instruments. Now juxtapose that with the closed tube. And when we say closed tube, we're just talking about one end being closed, because you got to get the air in there somehow. So one end is open, the other end is closed. So that means one end has to have a node. So this is your closed end right here. You can see that there's a node there. So that's a node, therefore closed end. And this side is the open end. You can see that the antinode is there. So what's the longest wavelength that can fit, the fundamental wavelength? Well, notice it's got to have a node here and then rises up to a crest. That's only 1/4 of the wavelength. That means I need to make the tube 4 times as large to fit the entire wavelength. So lambda 1 then is 4 times L. That corresponds to a fundamental frequency of the wave speed divided by that wavelength of 4L. What's the next largest wavelength that can create a standing wave in this closed-ended tube? Well, you can see that I've drawn it in pink, and it has a node here, comes up to an antinode back through 0, and then another antinode. Notice we would need to increase this tube length by another 1/4 to fit the rest of the wave to come back to 0. So the wavelength of the third harmonic that oscillates is 4/3 the length L. So the corresponding frequency of the third harmonic then is going to be the wave speed divided by this wavelength, and I flipped the 3 up into the numerator because it was in the denominator of the denominator. And so notice that this is also an integer multiple of the fundamental harmonic, but only odd integer multiples of the fundamental oscillate in the closed tube. So we lose the even harmonics in the closed tube. The open tube has the even and odd harmonics, but the closed tube only carries the odd harmonics. In other words, n equals 2 is not a solution here. N equals 4 is also not a solution, et cetera, et cetera, et cetera. So the even harmonics don't exist in the closed tube. So if you have any questions about this, please ask in class, and we will finish our discussion of Chapter 17 in the next video. We'll see you then.